Awesome. Cool. So today we are jumping around a bit, and this whole week I know is a bit different. The thing to bear in mind here is this is sort of like a crash course in like fundamental computer science. And again, the two reasons why this is important is some of it might come up in technical interviews, and this is sort of foundational knowledge that will set you all up to have like good careers and also be able to communicate with folks in the industry. And so we will get into some stuff that we will be practicing and getting our hands dirty with today and over the next several days. So this term complexity analysis is kind of fancy, and we're going to very quickly be just replacing it and talking about big O, which some of you may have heard of, some of you may have not. And the backstory here is, again, as you know, we're like the people in the 1950s coming up with the fundamental ideas of computers and computer science and discovering this stuff. I want to be able to figure out, is one program or two programs that do the same thing, is one way of doing it, is one implementation more efficient than another? And as you all get into your careers, this will be useful because there are always certain things that are just going to be less efficient and should be avoided. And the classic example is like nested for loops, right? Which I'm sure many of you have seen. So computers today are really powerful, as I mentioned, and we really don't have to think about a lot of this stuff on a day-to-day basis. They have lots of processing power and lots of memory or space for data. And if you're not familiar, by the way, technically speaking, you'll hear people talk about like storage and memory, or like hard disk and RAM. And without going into it too much, RAM, random access memory, are these little chips that sit close to the CPU. And just like we talked about with arrays and having stuff be contiguous and letting that be faster, the way that these chips are built, it's to be able to read stuff quickly, and also having it physically be closer to the CPU makes it faster. So, things that happen all the time, like, I don't know, moving a mouse pointer, that's what RAM is for. And then like, all the movies and music that I have, those live in storage, or the hard disk, what used to be an actual spinning magnetic hard drive and is probably now a solid state drive today. I think in reality it's much more complex, but just very quickly to break it down, that distinction. And again, these days we're very lucky, we don't have to think about this so much. And it'd be pretty hard to figure out an actual difference between like a really efficient program and a less efficient one, unless you really went out of your way to make a really inefficient program, or like just had to do an infinite loop or something. It wasn't always this way. Processor power and memory really were the limitations for the longest time. Like, like megabytes was a lot of space back in like the 1980s and like the early to mid 90s. Like the first time a 1 gigabyte drive came out in, I don't know when it was, probably sometime in the 90s, that was a big deal. Now, like having like 8 or 16 gigs of hard drive space or whatever is normal. These concerns are still relevant for us as professionals. You're writing a web app, you're writing Netflix. How long does it take for Netflix to work everywhere where there's a low bandwidth connection? Which is honestly in a lot of ways the United States, relative to like countries like certainly South Korea and Japan have way faster internet than we do. If you're Facebook, if you're Amazon, if you're the US government and the New York Times, you want the whole world to be able to load your app very quickly. And most people these days go online over their cell phones. One moment. Similarly, if we're dealing with something at scale, and scale is basically just like a term for very big, like something that scales to become very big. A Google search told me that Google processes over 99,000 searches per second. That's an awful lot of searches. You might, down the line in your career, maybe you work on internet things. Our smart light bulbs connect over Wi-Fi now, and like smart home systems, and people write web apps to manage them. And you'd be surprised how often you might see Python or JavaScript with Node.js pop up for writing one of these things. Energy efficiency is also becoming a bigger concern. So it's still important for us to think about program efficiency, even though in terms of like practical concerns, it's not directly relevant in this course for the most part. So what is complexity analysis? This is about how we can think about the performance of a program. I'll reiterate this later a little more specifically. This is thinking about programs where when the program input gets bigger, the program has to do more work, right? Like if all the program is doing is listing all the states in the United States, that's not a very interesting case for complexity analysis. It's not necessary because we always know there's always, it's like 50. I can't believe I'm blanking on this. And if one was ever added, it was ever a big deal, But if it's like find all the prime numbers up to 1,000, or find all the users with whose last name starts with L, well, then the input size, the number of users, prime numbers up to 1,000, 10,000, 100,000, the input size starts to matter. And so what is the efficiency? I really should have put efficiency instead of performance here. How long does the program take to run? How much memory does it take up? Time and space. And I had an awesome graphic here, which is totally not shown up. Let's see if we can find it. I'm so sorry about that. I got so excited about all my diagrams, and clearly this one, the link got lost in the mix. So there we go. That's the awesome like Doctor Who like diagram that we all were missing there. But to reiterate, how long does the program take to run? Time. How much memory does the program take up? Because as we saw, even though we don't have to deal with it, every time we create a variable, that does take up a tiny bit of memory. Space. Time and space, and the cool little graphic that did not make it in. As software developers, we care about worst case performance. If you worry about worst case performance, the best case performance takes care of itself. And the worst case performance is when stuff can start to eat up a lot of time and a lot of memory. This is really the essence of what I'll talk about a little bit later, which is called Big O, which is basically like, as my program input gets bigger, find all users whose last names start with L for 100 users, 1,000 users, 1,000,000 users, 100 million users, all the citizens of the United States, right? If we're working for the US Census, as the input size get bigger, that's really what we care about. So just kind of file that thought away. And also that's when bad things like running out of memory can potentially happen. And this term that we'll talk a little bit more about later, Big O, kind of encapsulates this. But basically, we generally are going to look at worst case performance to evaluate program efficiency and compare it. This slide here, I apologize. I needed to cut this one in half. This one is a bit too big. And in fact, I'll just pop over here. because I think this probably easier to read this way. And in fact, my guess is my next slide might not be in there. But things we don't care about, real numbers and details. Again, this is all sort of abstracted. We're interested in the efficiency of the algorithm that we write. So we don't actually care how many milliseconds, how many CPU cycles, how many bytes or whatever this stuff takes up. We're interested in sort of like an imaginary computer running this program. And let's see if this image shows up as well, or if this one was busted. Yeah, so I'll probably just run with this. So there's this great quote by this computer scientist, Edgar Dijkstra, I'm probably getting his name wrong. And it's a little abstract, but it is a good quote, and it is good food for thought. Computer science is not more about computers than astronomy is about telescopes, or biology is about microscopes. Science is not about tools. It's about how we use them and find out when we do. As software engineers, it is mostly about the tools, but just like if we're a mechanical engineer, it behooves us to know some physics. It's helpful for us to know some computer science as well. Dijkstra also thought for computer science education, like people shouldn't touch a computer for the first 2 years and just be like writing out like these symbolic logic sort of programs on pieces of paper, which is a little bit extreme. So as software engineers, we absolutely will care about real world performance. You will run your program, you will like grab data on like how long it took or how much memory it takes. That is something that as you get into your careers, you'll care about. But that's not done this way with like big O and complexity analysis. That's usually done by like you run the program with data, and then you record like real world measurements on things, right? We're interested in, let's call it like an ideal apples to apples comparisons of algorithms, different ways to write a program. So today we're really sort of computer scientists. So space complexity, how much memory a program uses when it runs. This is less common. It probably won't be asked about in technical interviews. People usually focus a bit more on time complexity. In this course, we're not going to talk about space complexity much after today. It is a useful concept. If it does come up in a technical interview, it will probably be some problem involving like in array replacement or in list replacement, which many of you may have seen in a programming problem where, you know, you're modifying some stuff in an array. Maybe you create a new array, and maybe the question is, solve this, but don't create a new array, modify it inside the array or inside the list, right? And in fact, that's one way to think about space complexity right there. And let's briefly talk about this a little bit. And just very quickly, can someone just maybe give me like a quick reminder, like how does an array work in computer memory? Like what distinguishes an array?
Only one data type and a fixed amount of units of that data.
Yeah, you got it. And each thing is right next to each other. They're all next to each other in memory. It's like addresses of houses on a block. If I know the address of the first house on the block, I can figure out the address for the third house on the block, the fourth house, the sixth house, and so on. So our problem that we're going to go through, that's a nice little experiment, is let's say just we have some integers, an array of integers, or really you can think of it as a list if you want, because we're not going to have to worry about like declaring sizes and stuff like that. But I'm just going to use the word array. Let's write a program to double the value of each element in this array. So 1 becomes 2, 0 stays 0, 14 becomes 28, and so on. And actually talking about this as an array, how much space does this array of 5 integers take up? Actually, I will maybe pop back to my thing here.
That'd be 128 bits.
How did you come to 128 bits?
Each integer I think takes 32. Right.
Got it. So 32 times 5.
Yeah, which is actually not it's actually 160.
Yeah, 160. That's certainly a reasonable guess. I apologize. My slide deck seems to be a little busted. You did kind of exactly what I'm going to talk about now, which is really we're just going to estimate and make stuff up. Because with like big O and complexity analysis, we don't care about real values and we don't care about real computers. We're thinking about imaginary computers, so we can just look at the efficiency of one algorithm versus another. I'm not going to worry about, does Python version 2 implement lists more efficiently, or would Python version 3 implement lists more efficiently than Python version 2? Would Java do this better than Python or JavaScript? Like all of that kind of goes out the window, because all we want to think about is the algorithm and how efficient is the algorithm. So exactly like you did, like most of the time, and even for the real world, we usually just estimate and make stuff up. And that gets us shockingly far. And this is actually a really important skill for technical interviews as well. So along the lines of what you were saying, I'm going to make it even simpler. Let's say an integer just takes up 1 byte or 8 bits, right? So like 8 zeros and ones like this, or this, or this. Let's not worry about fixed size arrays. Let's just say an array of length 3 integers, 3 bytes of space, an array of length 3 million integers, 3 million bytes of space, which is 3 megabytes, by the way. So an array of length 5 bytes, simple. An array of length n, how many bytes? Not a trick question.
N bytes.
Yeah, thank you. Exactly. We got it right there on the board. So does that feel good for everyone? Hopefully that doesn't feel too weird or anything, because it's not meant to be tricky. If you're like, duh, that is absolutely the intent. If you're like, there's one piece of this that I don't get, that probably means that I haven't been explaining this very well. So I would love any and all questions. Cool. People feeling good? Cool. So this problem, this space complexity problem, and what I'm doing here is using some really straightforward cases to talk about this. And then in a little bit later, we'll talk a little bit more about big O and really kind of dive in. So our task is to double the value of each element in here. 1 gets turned into 2, 0 stays the same, 14 gets turned into 28, and so on. Here's one way to solve that problem. And can everyone read this code okay and see it okay? Cool. Would people like me to put this in VS Code, or is this an okay way to read and talk about this right now? Cool. Okay. So this is relatively straightforward, right? We're going to create a new array, or it's a Python list, but we don't care. We're calling it an array. We're going to go through the existing one. For every number in there, we're going to multiply it by 2 and add it to our new array and return the new array. Right? Create a new array, iterate through the old one, double everything and add it to the new array. So how much space, how much memory does that algorithm, does that program take up? And I did kind of put the answer here now that my slide deck is a little busted.
It'd be double.
Yeah, exactly. We've got two arrays of the same size. Every integer takes up the same amount of space. I don't care if it's 1 or 100,000, it takes up 1 byte. I don't remember the limit of the biggest possible integer for 1 byte. So again, this is a pretty straightforward example, but this is why I wanted to talk a bit about, excuse me, computer memory and arrays, so we can start talking about time and space complexity. So Brian, yes, if we have a list of an array of 5 elements, we double it and multiply it by 32. Totally. If we have n, it's going to be 2 times n. Well, the 32 we don't even need to worry about. And so the next step here is, let's not even pretend to make up like how much space an integer takes up, like 1 byte, 32 bytes. Let's just call that like 1 unit of stuff. Because again, this is an imaginary computer. We're interested in comparing algorithms. If we really cared about the actual physical amount of space, we would run the program and then like run some other program to see how much actual space it took up. We're not interested in like real world numbers here, if that makes sense. We're interested in like an abstract imaginary implementation. So obviously, like, the bigger that n gets, the larger our array is, the more space the program takes up. And this was a question that I asked, and the answer is no, right? Does the size of a specific integer matter? It doesn't. And the golden rule here is we get to make all sorts of assumptions that we want, which is awesome. And that's like the fun part of this. So let's pretend this happens during a technical interview. And this is really common in technical interviews. You do well, and the interviewer throws more at you. So we're all doing the interview, and the interviewer's like, great job. Can you improve the runtime performance? Specifically, can you maybe like make this program more space efficient? Or is this the most space efficient version of this program possible? Any thoughts? Can we make this program more space efficient?
Definitely.
Awesome.
Yes, we can.
How? Yeah.
By altering the array in place.
Yeah, exactly. We create a new array and we stick all the stuff in it. If instead we don't create a new array and just modify the existing values, that takes up less space. Right? We modify the array in place. So here's another implementation of that same problem, which is not create an array or make new copies. And again, I did this in Python. Obviously, we're working with lists since we're using all this list related stuff, but we're pretending, we're pretending this is sort of like an array. And again, we're really interested in thinking about algorithm efficiency in like an imaginary sense. And even in school, I did all this in Java, and we didn't worry about like the real world performance of all this stuff because we're focusing on the concepts here. So we go through our array, and then for each element, we modify it in place, and then we return the array. And so what's the space complexity of this solution? if the last one was 2 times n, where n is the input size, the number of elements in the array, what's the space complexity of this one? Not a
N,
question. Sorry?
N,
Yeah, exactly. N takes up, if we want to say, every integer takes up a byte, it's n bytes. But n of whatever, or just plain old n. Can we make this program any more space efficient than we already have? Is this the most efficient implementation of this algorithm with regards to space complexity?
Yes, because you can't go lower than n.
Yeah, exactly. Like the input, the stuff that we're looking at itself is n. We've got to return that array. We can't make it any smaller. So this is a really simple example, but this is like the analysis in complexity analysis. Like we've taken a really simple case, and it's not quite proven, right? It's not like we wrote out like some math, but we basically just proved that this is like the most efficient implementation of this algorithm that we can possibly make for space complexity. So just to summarize, you usually will see time complexity. If this array in place replacement is, there's always sort of like a couple, not like tricks, but like sort of common things that may or may not pop up, and this is one of them. So this is just a good one to remember, like, hey, like I might be asked to like modify an array in place, or like maybe modify an algorithm to modify an array in place or something like that. Cool. So I just want to see what questions people have, or if people have any thoughts. Okay, so time complexity is where it starts to get a little more interesting, and it's really where we're going to focus on. Just like we kind of just got to make assumptions and make stuff up for space complexity, we're doing the same thing for time complexity. I'm not going to worry about if multiplication is more efficient than addition. I'm not going to worry about if Python does modulo more efficiently than Java does. All operations are equal. They all take the same amount of time. And really, the operations that we care about are the ones that happen more when our input gets bigger. So, like, we don't care about how many nano or microseconds Python actually takes running on my MacBook to add 2 + 2. Again, as software engineers, we may end up caring about that kind of stuff for performance improvements, but we would just run the program to get actual data, and then they call it finding like the hot spot, like the worst performing spot. That's not what we're doing here. All the stuff that's not a core part of the algorithm, we don't care about. We care about the stuff that happens more when our input size gets bigger, right? When that n gets big, because that's what really drives up how long something takes. And again, like this is all basically one step, because we don't really care, and we're interested in comparing the performance of 2 different implementations as its input size gets bigger. We care about what happens the most. That's usually in the loop that happens more when input size gets bigger. We care about how often that happens. So let's look at our problems that we just did, but let's talk about their time complexity. So I can't quite fit them both in here on the same page, but I can maybe. There we go. Is this readable for people? Cool. So what's the time complexity of this first one, where we were creating the second array, right? If our input is n, like how many operations for an input size of n does this program do? For an array of length 5, how many steps does this program have?
It does 5.
Yeah, it's just got 5. And if our array was of length 50, it would have 50 steps. And if it was 5,000, it would have 5,000 steps. So for an input size of n, it's got n steps. We don't care about declaring, this other array that only happens once. Let's look at what gets bigger as the input size gets bigger. We don't care that we multiply and then append because we just count all of that as one operation. So this is really the only thing that we count. And this happens n times, basically the length of the array. We don't care about the return statement. And then what about for our other implementation, the one that was better with space efficiency? What's the time complexity here? How many steps does it take for an array of length 5? Not a
Still
trick,
n.
Megan, exactly. It's still n, right? We've got the one array, the one operation inside there. As our input size gets bigger, this gets bigger. There's no, it's directly linear. It takes n steps. And I sort of wrote out what I just said here, but we usually want to look at the loop or the stuff that happens more when the input size gets bigger. We really don't care about all the nitty gritty. So each of those algorithms takes n steps. They both have the same time efficiency. And this is a good example of you'll often have to make trade-offs. And I do apologize. Let's see if my slide deck, how we can do here. Yeah, my slide deck needs some love. I apologize. Trade-offs are pretty common. Sometimes you have to trade space for time. Sometimes you have to trade time for space. And there's no one right answer. It's all about what am I trying to accomplish. A Python dictionary, it might take up more space than a list. I don't know, but it's a reasonable thought. But it's certainly faster to find something in a dictionary if you know the key. Or maybe I want a list and I make a dictionary too of the stuff in the list so I can find things really quickly, even though that means I've just doubled the amount of space I take up, but now I can find things really quickly, right? So on a practical level, you all don't have to worry about this for the programs that you're writing in this class. It is good to be aware. And also to understand that there's not like one right answer and there's no most efficient algorithm, because we just saw that our most efficient algorithm for space complexity was exactly the same in terms of time complexity. So it's kind of all about what are we focusing on? What do we care about? And searching versus sorting versus inserting are the classic trade-offs to be made here. Like if you want to search through something really quick, you might need to add it, like make more indices and take up more space, which maybe means that it takes more time to insert something. Let's look at a somewhat more interesting time complexity problem here. Let's look at an array of integers. Let's find out if there are any duplicate integers. Right? If the integer 2 pops up in there more than once. And again, I apologize that my slides are a little busted, but I think this one is relatively straightforward. If I just want to print every element in an array, if I just want to print every element twice, how long does it take? It takes, if n is the number of items in the array, we're just going to say it takes n. So this print elements twice problem, right? Whatever the size of our array is, that's the time efficiency. I don't care that I'm printing twice. I'm just going to count that as one operation. Does that make sense to everyone? Cool. Yeah, what we care about is the thing that gets bigger as our input size gets bigger. So let me make this. In fact, let me just copy this over here. And it really hates. Yeah, it might be easier to just hang out over here where we don't have all the squigglies. So here's a relatively straightforward implementation of finding like a duplicate item. Let's go through every item in our array, but then let's look through all the other ones. Right, so I start here, I start on 1, but then I do another loop, an inner loop that starts right here on 2, and I'm comparing this to all the others. So I compare 1 to 2, then I compare 1 to 3, then I compare 1 to 4, and 1 to 5, and so on. And do folks have questions around this implementation here? Does this sort of make sense as to what's going on? And would people like me to run this, by the way?
Run it.
Run it. Let's do it. So let's see. I suspect most of these squigglies are just honestly not sure what's causing them because it should run just fine. Yeah, let's see what. I'm so sorry about these. I will figure out a way to turn this off. I turned it on because I like the strictness when I'm actually programming, but it's a lot of like small best practice stuff. Like almost all of these are about you should add a comment string or you should implement this in a slightly different way because Python considers that better. So I apologize. But in fact, let's add a print statement so we can see exactly what's going on here. Print, let's just do an F string and we'll do comparing our sub I. And if I didn't screw anything up, there we go. Comparing 1, right? That's our outer loop. And here's our inner loop against 2, 3, 4, 5, 6, 7, 8, 9, and then finally 1, and finally we get true. So what's the time complexity of this algorithm? How many steps did this take to run for an input size of 11? So for that actual input of 11 things here, how many steps did this take?
Maybe 12.
Well, let's see. I've got my outer loop did one thing, right? I don't even know if we could say it did one thing actually, because that's just the print statement. It's really, I think, in fact, let me refactor this. I apologize. This is actually so the reason I'm rewriting this is really the thing that we're looking at. If I'm going to count something as an operation, I think it should really, well, we do want to know how many times this loops through and how many times this loops through, but this is kind of the easiest way to track that, right? Because like this is what happens every time, all the time.
Shouldn't the print statement be above the if statement?
Yeah, you are totally right. Thank you, Megan. I just, in fact, as I ran, I was just like, wait a minute. So this really, like, this is our operation that we're counting. And it happens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. Right, and then we get this true returned at the end. So question, what if instead of 1 being at the end of this list, it was at the beginning? How many times would this have run?
Twice.
Yeah, once or it goes, we enter into this loop, we enter into this loop, we do the one comparison. So once or twice, depending on how we want to count it. This is a really good example of best versus worst case performance. Same algorithm, huge difference in performance depending on if the duplicate is at the beginning or the end. Huge difference. And this is why generally we care about worst case performance for like performance analysis and time complexity. Because the best case scenarios, those are easy. So in terms of how to think through this, we just saw that we can kind of run a program and print this out. We saw with 10 steps, it takes 10 times. Another way to do this is let's come up with a really simple example. Let's just do 1, 2, 3, 1. And then we can easily think through this. We could also use the VS Code debugger if we wanted, but I've gone ahead and I've kind of written out like what's happening here. I do want to show you all the VS Code debugger, but I think it won't be this morning, though maybe a little later. And this is really how you should analyze these kinds of problems. When you're working on stuff like this, come up with a really small input size, write down exactly the value of everything, and step through the program just one step at a time. And when you're coming up with these experiments, you also want to think about, was my test data, was that like best case? Was that worst case? Well, that was the best case. If we stick the 1 at the end, oh, I'm sorry, I may have rewritten something here. Oh, and yeah. I apologize. I got a little confused. As bad as this is, because we compare 1, we don't get here till we find the duplicate. This is actually worse, where the 3 is here and then the other 3 is here. And actually, could someone explain to me why, if we're looking for a duplicate, as bad as this first array here is 1, 2, 3, 1, why is this second one worse?
because it'll start comparing 1 to everything and it runs through the whole list. Then it compares 2 to everything and it runs through the whole list. And then finally it compares 3 to everything, which is at the end of the list.
Yeah, exactly. Thank you, Cody. Like here, while it sucks that for like our inner loop, we have to get all the way to the end to find the duplicate one. At least the other duplicate was at the beginning. Here they're both at the end. Here we look at one, we compare it to everything, nothing. That's as long as it took to find the duplicate in this one. Here, 2, nothing. Then we finally get there to 3. So the program has to loop all the way to the end. Frank, yes, sir.
I might be getting ahead of this, but it's something that I saw while running similar loops in JavaScript. Would it still be the worst case if you made the loop run through the array backwards?
That is a good question. The answer is yes, because we have no guarantees about where these things are. So if we run through everything backwards, our worst case would just be the duplicates being up front, if that makes sense. If I'm understanding your question correctly. Is that what you were thinking, or were you thinking of a different approach?
Yeah, that was what I was thinking.
Got it. Yeah, that is a good thought. And there are times where we can use like techniques like that. But in this case, the problem is that we really have no way of knowing where the duplicates are. So there are, I see what you're saying, because if we run through backwards and maybe we somehow get to catch that case, it might make a difference. That would be interesting to dig into a bit. That does, I think, get a little out of scope though. And yeah, I'm gonna pause myself there. So that is an interesting thought, but it gets a little out of scope because it gets into really what this is all about, which is comparing different implementations of algorithms to figure out which one is more efficient. So I'm gonna jump through this stuff a little bit because we've been talking about it. But I would argue, like, if we wanted to be able to express like our worst case performance here, like for this current algorithm, it's the number of times we go through the inner loop times the number of times we go through the outer loop. And to boil it down here, it looks something like this. And it looks like my little backticks got screwed up. But if n is the number of elements in the array, the length of our array, we got to go through pretty much. I might need to throw in a -1 in here. I might have gotten something wrong here, but like for the inner loop, we never go through the very first element. For the outer loop, I might need to throw in a -1, but in the essence, it comes to the same thing because, again, I apologize for these backticks. But what we really care about is the n squared. I actually really don't care about anything else. If n is the number of elements in the array. And the reason we don't care about anything else is because if our input size is 1,000,000, if we've got 1,000,000 integers, well, 1,000,000 minus 1 times 1,000,000 is 1,000,000 squared minus 1,000,000, which is still massively huge. So as the input size gets bigger, we really only care about like the value that increases the most. There's some math term for that, but I'm forgetting it at the moment. But this is sort of what big O is, that we care about the thing that gets the biggest, the quickest, because if we get really big, nothing else really matters. Like if I've got 1,000,000 integers, I don't care about the minus n, I care about the n squared. And I want to check in and see if that kind of makes sense to people. Or what questions people have. Cool. So again, the thing to think about here is when we're, designing this program, I don't need to know the exact number when I'm choosing algorithms. I just want to know the scale. I want to know the relative difference. Or as I kind of said it here, bigger than a cardboard box, but smaller than a shipping container. We're interested in the order of magnitude, right? What gets biggest the fastest, and we're really interested in worst case performance, and that's kind of what Big O is. So, and we're going to take a break, and then I'll talk about Big O a bit, and then that's kind of what we'll be doing for the afternoon is a little bit of complexity analysis. But I want to show just very quickly a somewhat more efficient solution to that same problem. And the solution that I chose to show, we actually have to sort our data first. Because the worst case scenario is when the duplicate is at the end. And Frank, you threw out like an interesting technique here that we could try of, what if we maybe have one array move forward and the other move backwards? And I think that would help, because if one is moving forward and one is moving backwards, then that probably helps because we get to the end first, right? So it eliminates that particular sort of worst case scenario. I don't know if then there would be some other worst case scenario. It might be like if they were both in the middle, right? And that would probably still be a bit more efficient. So you might be right there. But point being is that the worst case scenario is what is going to take the loops the longest to find. And if we sort, then this whole problem goes away, right? If we sort, then all of this becomes dramatically simpler. Even with sorting, though, it's not a perfect solution, right? This is a sorted array. The duplicates here are right at the end. And in the current implementation, we're both just move forward. And Frank, here, I think your approach would help. So I think you were right. This is still our worst case scenario, right? So sorting doesn't necessarily like solve everything all the time, but it certainly can help. And here's a good example of an unsorted array where the duplicate is a 3 and we've got one here and one over here at the end. But if we sort it, then they're over here in the middle and we're more likely to find them. So how long does the sorting take? Well, I don't know. And I'm just going to declare that, let's say it takes some number of steps, and maybe that sorting is less than going through absolutely everything. I'm going to abstract that part away. And once this is sorted, our algorithm gets a little easier. And in fact, I think I need to fix this, and this should be a plus instead of a minus, because the idea is to compare 1 and 2 and so on and so forth. So there's actually a couple things that I actually should improve. So I apologize. This has a couple. I think this code right here has a couple issues, actually. Yeah, I will fix and update this. But to sort of show and walk through what we can do with a sorted algorithm is, I don't need a nested loop, because once it's sorted, like if I've got a 1 over here any one is going to be right next to it. So I just have to compare 1 to the thing right next to it, and then I can move on. So I can compare 1 to 2. In fact, I can even jump over then, and I can look at 3, and then I just need to compare 3 to whatever's next. And I can move on. So I don't need a nested loop. So then my runtime performance becomes a whole lot closer to n. And I think I do have a goof in here that I want to fix, so I apologize about that. But the main thing that I want to demonstrate here is that like one common approach to make the efficiency of stuff like this better is sorting. And that like we don't always have to, like this sorting operation we can abstract out, and we can just say, hey, this takes S steps, and that's less than the length of the list itself. And that's okay to make that assumption and do that as well. So let me just pause here and see what questions people have, and then we will take another break. Oh, Halsey, I just saw your question in the chat of would the worst case be if there are no duplicates? That is a very good point, and essentially, I believe yes. Because if there's no duplicates, the algorithm is going to run until it gets all the way through everything, which is, yeah, I think you're correct. That's going to take the most amount of time. That's a very good point, actually. I should have mentioned that, so thank you for asking about that. Okay, let's take a 15-minute break, and then when we come back, we'll talk about Big O, which is what this is sort of like a prelude to, and we'll actually like apply this to a problem. So we'll do a little taste of kind of stuff that you guys will be working on this afternoon. Thank you, everyone, and see you in 15 minutes.
Actually, and Adam, sorry.
Oh, what's up?
Yeah, I actually have a question regarding this note. So at the bottom, like for this like contains duplicate sorts, I believe the note says the time complexity is no, it's at the bottom. Can go down. Yeah, here is perfect. It says our time complexity is then S times n, but I think it should be S plus n in this case, because it's like taking
Yes.
one sort plus one for loop.
You are so right. I'm so sorry about that. That's an excellent point. Thank you so much for mentioning that.
Yeah, no problem.
Yeah. So folks, I totally screwed up in writing this here. And what Shannon is saying is that, hey, like we sort and we loop, but like if I don't sort for every time I loop, right? Like this multiplication, that's what you see like for a nested for loop, or when like the number of times that we loop depends on the number of times that we sort or whatever. But that's not the case. You know, we sort and that has its own time complexity S, and we loop. So this should be a plus. I'm really sorry about that. Does that make sense to folks? Like, for instance, if my array has, let's just say like length 10, and let's say sorting takes 10 steps. I've got 10 steps here and 10 steps here. And I would add those things together to get the total amount of operations. Or if I have a array of length 3, it would be 3. Because I do this 3 times, and then I do this 3 times. So I'm looking at 3 plus 3. Yeah, in fact, I will fix that right now. That is a bit of a goof. All right, folks, awesome. Let's take a break and see everyone in 15.